Good morning, students. Today we are going to read the lecture number 2. That is force on a current carrying conductor. In the topic of magnetism in the subject of physics O levels. So concentrate yourself. The first thing that is for the today's lecture is, why does a current carrying conductor experience a force when placed in a magnetic field? So here we are going to start. Fleming's left hand rule only helps us predict the direction of the motion of the force. To explain why a force acts on a current carrying wire placed in a magnetic field, we must examine the combined magnetic fields due to the current in a wire and a magnet. So here is the field that is created by the current. So look now, field due to the current in a wire, and this is the field due to the magnet. So these two fields will be applied on the wire, okay, through a wire and the magnetic field due to the magnet respectively. And these are the separate magnetic fields of the current flowing through a wire and of two magnet poles. So this is the field due to the poles of the magnet, and this is the field due to the current. Figure C shows the superimposed field pattern of the magnet and the current carrying conductor. So this is the superimposed field pattern of the two fields, that is one from the one due to the current and second due to the poles of the magnet. So look now, superimposed field pattern of A and B, and that is wire with a current flowing into the paper. So the direction of the flow of the current is into the paper, that is away from you. Figure D shows the combined magnetic field when the wire is placed between the magnetic poles. So now you can see when the wire is placed between the poles of the magnet, so this is the direction of the force, because the field due to the current will squashes the field due to the poles of the magnet, and this squashes will apply a catapult force on the wire. This is the direction of the force. So look now, combined magnetic field when the wire is placed between the poles of the magnet. From D we can see that there is a strong field on one side of the wire at A. So here will be the strong field, and the other end at B there will be a weaker force, and this stronger force will push the wire in a direction. So look now, at B the magnetic field lines of the current oppose those of the magnet, making the combined field weaker. Okay, so it means at the B there will be a weaker force, and at A there will be a stronger force. So look now, this is the field due to the current, and this is the field due to the magnet, and due to the current squashes the field due to the poles of the magnet, and this squashes will apply a catapult force on the wire. A force then acts on the wire from the stronger field to the weaker field. Okay, the next thing that we are going to read in the lecture is force on a moving charge in a magnetic field. So this is very easy now, because you have understand the lecture to a great extent now. So we have just learned that a current carrying wire experiences a force when it is placed in a magnetic field. We also know that the current is the flow of the electric charges, free electrons, in the wire. Here we will examine the effect of the moving electric charges in a magnetic field. So look now in the figure. Below, the crosses represent the part of the magnetic field. The direction of the magnetic field is into the plane of the paper, away from you. So this is the point to be noted, that magnetic field is into the pole, away from you. Okay, direction of the positively charged particle before entering the magnetic field. So this is the direction before entering into the magnetic field. This is a positively charged particle, and this is the magnetic field into the plane of the paper, and path of the positively charged particle, part of the circle. So this will be the path of the positively charged particle, and look now, this will be the direction of the force. So here you can see This is Fleming's left hand rule. So this is the direction of the positively charged particles, and this is the direction of the field away from you into the paper, and this will be the direction of the force. So this is the direction of the force. So this is the Fleming's left hand rule. A positively charged particle in a magnetic field is deflected upward in a circular path. So this is the point to be noted, that when the magnetic field is away from you into the paper, the force that will be acted on the positively charged particles will be in upward direction. So when a beam of the positive charges, for example protons, enter the magnetic field region, the beam is deflected upward in a circular path. This is because the moving charges experiences a force perpendicular to its direction of the motion. The direction of this force can also be predicted by Fleming's left hand rule. So this is the thing. This is the left hand rule. This is the Fleming's left hand rule. So the direction of the force can be predicted with the Fleming's left hand rule. We take current to be in the direction of the beam. In the direction of the beam of the positive charges. However, if we have a beam of the electrons, so look now, the things will be reversed now, because this is a positive charge. So if the force is acting in the upward direction, so now if we have a beam of the electrons, so the direction of the force will be in downward direction. So look now, however, if we have a beam of the electrons or negatively charged, we follow the conventional current direction, which is opposite to that of the electron flow figure below. So look now, here is the electron or negatively charged particles. So the magnetic field is into the paper. So the remaining of the conditions are same, only we have changed positive charge with the negative charge. Now the direction of the force will be in downward direction, because we have to take the direction of the current opposite to the flow of the electrons. So look now, this will be the rule now. The force will be in downward direction. So a negatively charged particle is deflected downward in the same magnetic field. Okay, here is another case. Look now, the positively charged particles are taken again, but now the magnetic field outward from the plane towards you. So definitely the direction of the force will be reversed. That will be in the downward direction. So look now in the figure below, the beam of the positive charges or the protons enter a region of the magnetic field which is directed out of the plane of the paper towards you. The beam is now deflected downward because you have reversed the direction of the magnetic field now. So the direction of the force will also be reversed. The positively charged particles is deflected downward when the magnetic field is reversed. Okay, the next thing that we are going to read in the lecture is the forces between the two parallel current carrying wires. So again, this is very easy topic because you have learned more of the concepts in this lecture. So when two current carrying wires are placed parallel to each other, we would expect a force to act on each wire. Figure below demonstrates the forces that exist between the two parallel current carrying strips of the aluminium. So look now, here is the thing. When the current in each conductor flows in the opposite direction, the strips repels. So this is the point to be noted. The concepts are coming later in the lecture. However, when both currents are in the same direction, they attract each other. So the point to be noted is, when the current in each conductor flows in opposite direction, the strips repels. But when the both currents are in the same direction, they attract. So this is the point to be noted. So look now, unlike currents that is opposite direction, so they will repel, and like currents in the same direction, they will attract. So this is the point to be noted. So here is the concept that is in purple color. Current in opposing directions cause repulsion, and currents in similar direction cause attraction. We can summarize the forces between the two parallel current carrying wires as, so like currents same direction, they will attract. Unlike currents opposing direction, they will repel. Okay, we explain this. So this is the explanation now. We explain this phenomena by looking at the combined magnetic fields due to the both wires. So here you can see that the combined magnetic field due to the currents in the opposing direction. So one's field is in this direction and second field is in direction of the current carrying coils. So it means they are in opposite direction. So you can look now at this stage, they will repel each other now. So look now, they will repel each other now because the current are flowing in the opposite direction. And here you can see the combined magnetic field due to the currents in the same direction. So this is the field due to the current in one wire, and this is the field due to the wire in the second due to the current in the second wire. So the current are flowing in the same direction, and at this stage you can see they will attract each other. So the thing is, like current attract with force F, there is a tendency for long magnetic lines of the force to be as short as they possibly could. So this is the force of the attraction between the two current carrying wires. Current is flowing in the same direction, and the unlike currents repel each other. You can see from here now. With force F, crowded magnetic lines of the force in the same direction exert a sideways lateral force on each other. So here you can see they will repel each other. Since the flow of the negatively charged electrons is opposite to the flow of the current, figure A is equivalent to figure B when applying to the motor rule. So here you can see. So this is the thing. When applying the motor rule on electrons, it must be kept in mind that the second finger must point opposite to the electron flow as shown in the figure B. So here you can see this is the current. So we will apply like this because this is the direction of the flow of the negatively charged particles now. So it means the force direction of the force will be in this direction. So here you can see this is the force on the electrons, this is the field, and this is the current. Here are some key ideas for you people. When a current carrying conductor is placed in a magnetic field, the conductor experiences a force. The second concept is the direction of the force can be determined by Fleming's left hand rule. And the last idea for you people is for two parallel current carrying conductors, current in opposing direction repel and currents in similar directions attract. Okay, the next thing in the lecture for today is force on a current carrying rectangular coil in a magnetic field. You will be able to explain how a current carrying coil in a magnetic field experiences a turning effect and how the turning effect can be increased. Discuss how this turning effect is used in a simple electric motor. Describes the action of the split ring commutator in a two-pole single pole motor and the effect of the winding the coil onto a soft iron cylinder. So you will be able now. So here is the explanation now. Concentrate now. If we place a still wire coil, for example coil ABCD in the figure below. So here you can see this is ABCD between the poles of the strong magnet and pass a current through the coil. We will observe a turning effect on the coil. If the current is flowing clockwise in the coil, so if we see from P position and if the current is flowing in the clockwise direction in the coil ABCD, the coil will experience a clockwise movement about the axis PQ. So if the flow of the current is clockwise, the movement of the movement that will create in the coil will also be clockwise about the axis PQ. Again, we will look at the combined magnetic field due to the current carrying coil and the magnet. Figure below shows the plan view of the magnetic field produced by the rectangular coil superimposed on the field of the magnet. Figure below shows the combined magnetic field and the resulting forces. So here you can see this is the field that is created due to the current, and this is the field that is created due to the poles of the magnet. The field due to the current is actually squashes the field of the field created by the poles of the magnet, and that will create a catapult force on the wire. The sides of the wire AB and CD experience equal and opposite forces. Do you think that the direction of this pair of the forces can be predicted by Fleming's left-hand rule? These two forces produce a clockwise turning effect when viewed from the P. If we view from the P, and if the flow of the current is in the clockwise direction, the movement that will be created in the coil ABCD will also be clockwise. To increase the turning effect on the wire coil, we can, so these are the two factors which actually affect on the turning effect of the coil. Is if we increase the number of the turns on the wire, so more the number of the turns, more will be the turning effect of the coil, and if more the current in the coil, more will be the turning effect of the wire also. And vice versa also applies. If we decrease the number of the turns in the wire of the coil, there will be decrease in the turning effect of the wire coil, and if we decrease the current in the coil, that will decrease the turning effect of the wire coil also. Okay, this turning effect on a current carrying coil in a magnetic field has a very important applications, and here we are going to read the applications of the current carrying coil. The direct current motor. The DC motor is used commonly in the toy cars, DVDs, and hard disk drives. There is also the alternating current, that is AC motor, which is used in many electrical appliances like electric fans, hair dryers, and washing machines. So here are some applications of the alternating current, and some applications are of the direct current. So this was the lecture, students. I hope so this will be much more easier for you to understand now. So read this lecture again, understand it, learn it, and make your notes. Thank you so much.